In free space optical communications, achieving precise pointing between the ground station and the satellite is crucial for establishing a link. However, this is easier said than done, as pointing errors can arise from various sources. So let's explore specific challenges. A specific challenge called the point-ahead angle. So let's first recap the main cause of pointing errors in FSO systems. So it's inability to determine the exact direction. This can stem from uncertainties in satellite position or limitation in the pointing instruments. Afterwards, we have pointing instrument limitations. Those are imperfections in the pointing mechanism, which can introduce errors. Afterwards, we have transmitter and/or receiver relative motion. If either the ground station or satellite is moving, maintaining precise alignment becomes difficult. Atmospheric turbulence can distort the beam and cause it to wander off target. And finally, point-ahead angle. This is a unique challenge arising from finite speed of light and relative motion of the satellite. So what's point-ahead angle? So finite speed of light doesn't travel instantaneously. It takes a finite amount of time for the beam to reach the satellite. During this transmission time, the satellite moves along its orbit. The beam needs to be aimed slightly ahead of the satellite's current position to ensure it hits a target when it arrives. So here you can see that R1 represents the satellite position when the beam is transmitted from the ground station. R3 represents the satellite position when the beam actually reaches it. Theta L is the point-ahead angle, the angular difference between the satellite current position, R1, and the future position, T3. So how do we calculate this point-ahead angle? It can be calculated by approximating using the following formula, which is equals approximate to v, where is the orbital speed of the satellite, divided by the speed of light. So in the example provided, with a satellite velocity of 7.5 kilometers, the point-ahead angle is around 50 microradians. So what are implications for free space optical communications? The point-ahead angle is a critical consideration in a free space optical communication system design. Failure to account for it can lead to significant pointing errors and loss of communication. To address this challenge, free space optical communication systems employ sophisticated pointing and tracking mechanisms from the ground station side to continuously adjust the beam direction to compensate for the satellite motion. In conclusion, understanding and accurately calculating the point-ahead angle is essential for achieving successful acquisition and maintaining reliable communication in free space optical communication systems. In free space optical communications, establishing the initial link or acquisition often involves scanning process. So here we'll explore a common scanning strategy, the spiral scan pattern. So here we can see an image which demonstrates a spiral scan pattern. The ground station beacon laser beam systematically sweeps across the potential location array of the satellite terminal. The spiral widens outwards, covering a large area with each revolution. The goal of the spiral scan is to locate the satellite terminal with a predefined uncertain region. This region accounts for potential errors in the estimated satellite position and pointing inaccuracies. So here you can see a graph which illustrates two key factors influence the mean acquisition time of a single scan. So we can see that the larger uncertain area, the longer it takes to complete a scan and locate the satellite. This is evident in the graph as the curves shift upwards larger values of t theta. Higher pointing errors means the beam might miss the satellite even if scans are in the correct area. This increases the acquisition time as seen in the high curves for larger uncertainty values of sigma. So for a given pointing error, sigma, increasing the uncertainty area significantly increases the mean acquisition time. For a fixed uncertainty area, larger pointing errors lead to a dramatic increase in acquisition time. As you can see here, acquisition time increases with with increasing, for example, pointing error. So, key takeaways: spiral scans are an effective way to search for and acquire the satellite terminal in free space optical communications. The size of uncertain area and the pointing errors standard deviation are critical factors that directly influence the acquisition time. Minimizing these factors through precise pointing and accurate satellite position estimation can significantly reduce the time required to establish a link.